Today I'll be giving a quick lesson on RS configuration. It's something that I've gotten quite a few questions about recently, so I thought it would be a good thing to review, especially in specific circumstances that we'll get to later. Before we can talk about RS configuration, we need to understand what a stereocenter is. That's the only time that we use RS configuration. So a stereocenter is a carbon bound to 4 chemically unique groups. So each of these different R groups represents a chemically unique group, making this a stereocenter. If 2 of these groups were the same, say this was R2, so it matched this R2 group, this would no longer be a stereocenter. However, in this case, these are 4 unique groups, making this a stereocenter. Now, if I drew this molecule's mirror image, if you looked at this in a mirror, it would look like this. If I drew this molecule's mirror image and then I wanted to try and match these 2 molecules up, see if they were the same, if it's the same as its mirror image, well, I could slide my hand under this molecule and then flip it over. And if you did that, it would actually end up looking like this. End up looking like this. Or when I flip it over, now the third R group is going into the page and the H is coming out of it. Well, let's see if these are the same molecule. If I put this central carbon, our stereocenter, on top of this central carbon, that stereocenter, these 2 molecules will not match up. The R1 will match up, the R2 will match up, but the H is on top of the R3 and the R3 is on top of the H. That's not right. Well, if I flip it back over so it looks like this, and then I put this carbon on top of this carbon, yeah, the R3s will match up and the H's will match up, but now the R2 will be on top of the R1 and this R2 will be on top of this R1. So these 2 molecules are actually not identical. They're called enantiomers. In an enantiomer, these 2 molecules are enantiomers of one another, is a non-superimposable mirror image. Non-superimposable, meaning they can't match up. If you try to set them on top of each other to match them up, they won't match up. That's a non-superimposable mirror image, or an enantiomer. Well, like I said, these 2 molecules are different. So how do we differentiate between these 2 molecules? How do we differentiate them by name? We need to be able to call them something different so that as chemists we know which of these 2 molecules we're talking about. And the way we do that is by RS configurations. That's what it's used for. It's used to differentiate between 2 different stereocenters and the arrangement of these groups around them. So one of these molecules would be an R and one of these would be an S. So that way we could say this is the R enantiomer of this compound, this is the S enantiomer of this compound. The way that we determine whether it's R or S follows a simple set of steps. First off, we're going to assign priority to the 4 groups around the stereocenter based on atomic number. In other words, the higher the group's atomic number, the higher priority it's assigned. So let's look at a quick example. If we had a bromine bound to a carbon, bound to, let's say, an amine group, and then we have a methyl group and hydrogen. So let's assign priority to these groups based on the atomic number. Well, bromine has the highest atomic number out of all these groups. So it will get the highest priority number 1. Nitrogen, then we're just comparing these 3 groups. Nitrogen has a higher atomic number than carbon or hydrogen. So it'll be priority 2. Carbon is higher than hydrogen, so it'll be priority 3. And lastly, hydrogen is our only remaining with the lowest atomic number of atomic number 1. That's how we would assign priority based on atomic number. The next step deals with if there's a tie. If there is a tie, we go to the next atom out and apply the same rule. So let's draw another molecule, something that we can apply this rule to. Well, if we have the same bromine bound to, this time we're going to have a CH2 bound to an amine group. And up here we have a CH2, CH3, ethyl. And then lastly we have a hydrogen again. So again, bromine has the highest atomic number, but when we come to compare these 3 groups we say this is a carbon, this is a carbon. Wait, that's a tie. What do we do in that case? Well, we go to the next atom out and apply the same rule. So we go to the next atom out and say that's a carbon. Next atom out here is a nitrogen. Nitrogen wins. That means this is group 2. This would be group 3. And again, hydrogen is group 4. Hopefully that makes sense. A quick note about double bonds in these molecules. Say we had a molecule like this. Realize that that COH I just drew is actually an aldehyde. Sometimes it's difficult to see. So this carbon has 2 bonds to that oxygen. And we'll give a hydrogen again. Let's try and apply the same rule. So bromine again has the highest atomic number. Then as we're comparing these 2 carbons, will the carbons match up? Well, you have to go to the next atom out. This carbon is bound to oxygen through a double bond, whereas this carbon is bound to oxygen through a single bond. Well, when atoms are bound to other atoms, in this case carbon to oxygen through a double bond, that's equivalent to the carbon being bound to 2 oxygens. So a carbon being bound to 2 oxygens is more significant than a carbon being bound to 1 oxygen, so it's assigned the higher priority. The last thing we need to look out for is we always need to have, in order for RS to work, in order to get the correct answers, we always need to have the lowest priority group, or group priority 4, going back, or going away from us. So notice that in each of the molecules we've drawn so far, the H is on the dashed bond. It's going away from us. So that's good. That's what we want. We're going to address what happens when the H is not going away from us in just a minute. But for right now, we're going to finish learning how to do an RS configuration using the molecules we've already drawn. So once we've assigned priority and we've made sure that our H's are going away from us, or our lowest priority group, it's not always going to be an H, but almost always it will be a hydrogen that you need to be going away from you, at least for the purposes of the DAT. We trace with our finger from 1 to 2 to 3, so from highest priority to lowest priority, and we ignore 4. So we just trace from 1 to 2 to 3. If when we trace from 1 to 2 to 3, our finger is moving clockwise, that molecule is an R configuration. If it's moving counterclockwise from 1 to 2 to 3, that molecule is in an S configuration. And there are a couple different ways to memorize this. It always made sense to me to say that if it's clockwise, that's the right way for a clock to work, or the correct way. So clockwise is R, and counterclockwise is just the other one, S. I didn't really come up with a mnemonic for counterclockwise. I just remembered it wasn't R. It wasn't the right way for it to work. So let's assign really quick RS configurations to the molecules we've already drawn. Looking at this first molecule on the bottom left, bromine is 1, nitrogen is 2, carbon is 3, and hydrogen is 4. Again, we're going to ignore the 4, so we just trace from 1 to 2 to 3. You can see that this rotation here, 1, 2, 3, is counterclockwise. So counterclockwise is backwards to how a clock usually works, which is S. And just because I try to simplify things and draw these all in the same configuration, you can see that all of these will be S. We're going kind of the same way, 1, 2, 3, and all of these counterclockwise. 1 to 2, 2 to 3, 3 to 1. Again, we ignore 4. 1, 2, 3, that's counterclockwise again. And I'll give you one example where it's clockwise so you can see. What if we had something like this? Let's assign priority. Priority would be 1. Bromine has the highest atomic number. Carbon-carbon tie. Let's go out to the next molecule, the next atom. This is bound only to H's. This is bound to an oxygen. Oxygen beats a hydrogen. So this is 2, 3, and then the hydrogen's 4. But again, we ignore that fourth group for RS assignment. When we go 1 to 2, 2 to 3, 3 to 1, 1, 2, 3. That's right. That's clockwise, R. Okay, let's deal with the exceptions. This is where most students get confused. What happens when we don't meet the third rule? What happens when the lowest priority group is not going back? There's really only 2 options. It could either be coming forward on the wedge, or it could be in the plane of the board. And we address those two situations differently. But again, this is where so many students get mixed up, and it's actually not too difficult if you just remember these little shortcuts, these little rules. So let's draw a molecule we've worked with before, but this time we're going to put the H coming forward on a wedge. That's supposed to be an H. When the H is on the wedge, what we do is we assign priority the same as we usually do. Bromine has the highest atomic number, so it's a 1. CH2OH beats out a methyl group, and then the H is 4. But again, we're going to ignore that for when we assign RS. So let's draw our arrows. So we go 1 to 2, 2 to 3, 3 to 1. That is counterclockwise. That's an S. However, we realize our H is not where it's supposed to be, so we switch it to the opposite configuration. This is R. So again, let me say that one more time. We go from 1 to 2 to 3, and we see that it's S, but we realize our H is not where it's supposed to be. Our H is our lowest priority group. It should be going back on the dash, but it's not. It's coming forward on the wedge. So we say, okay, this is S, but our H is in the wrong place. It's on a wedge, so we switch it to R. You always just switch it to the opposite when the H is on the wedge, when it's coming forward. The other option, the only other option you can have for H is when H is in the plane of the board, and this is the one I've gotten the most questions about. Students get tripped up on this a lot. So let's draw the same molecule, but with the H in the plane of the board. CH2OH and our methyl group. What you do is you perform a switch. You simply switch this H with a group that is on the dash, and you put the group that's on the dash where the H was, and then you redraw. Let's redraw this, having made that switch. Having made that switch, the methyl group will be in the plane of the board where the H used to be. The H will be going back just like we like. And the CH2OH and the bromine stay the same. Now let's assign priority. Bromine will still be 1. CH2OH will beat out the CH3. And hydrogen will be last. Again, we're going to ignore that for the purposes of RS assignment. And it's now going back where we want it to go. So let's draw our arrows. 1 to 2, 2 to 3, 3 to 1. Okay, that is counterclockwise. That's a counterclockwise rotation. So it's S. But we remember that we performed a switch. Because we performed a switch, we need to change the configuration that we find. It's R. So this was S, but we remember, wait, I switched something in the beginning. So it's actually the opposite, it's R. But it's not the same as the wedge rule. You have to redraw the molecule, and then you have to find the configuration, and then you have to switch it. You cannot simply find the configuration of this molecule and switch it. You have to redraw it, find the configuration, and switch it. Like I said, in this case, just because of the way I've laid this molecule out, it may work to assign priority, find RS configuration, and then switch it directly without redrawing it, but that will rarely work. Do not do that. That's how students miss questions on the DAT with this principle. If H is in the plane of the board, you switch it so it's on the dash, find out the RS configuration, and then change it to the opposite. Hope that makes sense, and hope you guys enjoyed the video.